kind of a wasted like 5 minutes for people, and they'll be irritated with me. Okay, so we are on page 30, and we are looking at the formula 1/2 mv squared, and we're wondering how that affects the curves on model 3, the graph on the left. So this is that there are two graphs. This is a graph on the left, so we're looking for helium. So because it's all helium, we know that the masses are all the same, okay? So masses are all the same, but the temperatures are different. Okay, and what is temperature? Is a measure of the average what? Kinetic energy of the particle. Okay, so temperature is kinetic energy, essentially. And because we are increasing the temperature, that means the kinetic energy is increasing. And so we can see that at our lowest temperature, we have the peak is close, has the lowest amount of kinetic energy. Does that make sense? Okay. And then we have our highest temperature here. And one thing that you'll notice is that the actual peak, what's happening to the actual peak? It's getting rounder, the peak is getting rounder, and it is also, if we were to continue this upward, what's happening to it? It's moving to the right, okay? So the peak moves to the right. As the temperature increases, which should make sense because as temperature increases, the average kinetic energy increases. Now this represents the number of particles. What does the area under the curve represent? Do you remember that at all? Probably not, I'm guessing, because you guys didn't learn it and you've probably forgotten. Am I right? Okay. The area under the curve represents the total number of molecules. Okay. So if the area under the curve represents the total number of molecules, and we have our total number of molecules in this case is 1 million. Yes? So the total number of molecules is staying the same for all of these curves. So what we can look at then is we can look at this curve here, which ends way over to the right. You know, its highest kinetic energy is much higher than the highest kinetic energy of the lowest peak. So what we're having is this curve is getting, as temperature increases, the curve gets wider. But because the number of particles is staying the same, the height has to get lower because otherwise the area will not remain the same. Is good? Okay, so that's basically it for this one, okay? Now, here we have the kinetic energy of noble gas molecules. This time they are all at the same temperature. Energy is equal to 1/2 mv V squared. And we have helium, we have argon, and xenon. And what can you say about all three of those curves? Pretty much the same. We've got helium, which has a molar mass of 4 grams per mole. We have xenon, which has a mass of approximately 131 grams per mole. So, but because we are all at the same temperature, what can you say about the kinetic energy? They're all the same because temperature is a measure of the kinetic energy, okay? And so the kinetic energy diagram remains the same. However, what could you say about the velocity of these various things if their kinetic energy is remaining the same? Let's just compare helium and xenon. What could you say about their velocity? Yes, Rigel? Yeah. Exactly, exactly. So in order for kinetic energy to remain the same, and sometimes there's not enough room to write on these pages, so if you run out of room, feel free. There's free paper at the back, blank paper at the back of the room. I don't know why I'm writing this. I should write the same. For the kinetic energy to be the same, a lower mass particle must be traveling at a higher velocity. A higher mass particle must be traveling at a lower velocity. Okay, so that's what we've got from our curves there. Let us take a look at some of these other questions. Number 26, draw particulate representation of helium atoms at the 2 different temperatures below. Use arrows to illustrate the distribution in kinetic energies. Okay, so that would be like, what do they mean at the 2 different temperatures below? I'm going to assume we just have 2 different temperatures. We have a high temperature and a low temperature. I'm not sure what temperatures they're referring to. Let's just do low temperature and high temperature. I'm not sure I approve of this document completely. It's a little dodgy at times, so I might need to rejig it a little bit. So at the low temperature and at the high temperature, if you're drawing a particle diagram, basically you would draw some particles in there and you would be like, okay, at the low temperature, they're moving not very fast. Yes. But at the high temperature, you might still have one particle that's not moving very fast, but you're also going to have particles that are moving much faster and sort of medium speed. Okay, so you've got a distribution of, and maybe even at the lower temperature, you might have one that's kind of going at a medium speed, right? So you have a distribution of temperatures. draw particulate representations of two different noble gases. So let's do helium and xenon, and this is at the same temperature. So using those ones that we just did above as models, what do you think these would look like? So they're at the same temperature, but we have different, and I'll actually draw the helium as smaller than the xenon, just so you can kind of envision, like, xenon's heavier, right? Xenon's going to travel slower because kinetic energy is 1/2 mv squared. M is greater, therefore the velocity is slower. So we're like, okay, la, 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 la. But helium, the m is smaller, therefore the velocity is greater. Okay. Yoo-hoo! Okay, sorry. A student is presented with 4 bottles containing different gases. All samples are at the same temperature. So we have 1 mole, 1 mole, 1 mole. Oh, we got 2 moles of the CO2 in that third bottle. Okay, so we have O2, CO2, CO2, and helium. Which sample has the fastest average particle speed? And they're all at the same temperature. Yes. Yes. Because if we're at the same temperature, the particles have the same kinetic energy. I'm spelling particles with a K. That's all good. Okay, particles have the same kinetic energy, and kinetic energy is equal to 1/2 mv squared. Helium's mass is the smallest, so its velocity must be the greatest. Ah! Which sample has the highest average kinetic energy? Yes, all the same. I think it has to be like no, because it's the average kinetic energy. I will look that up because that made me think as well. I was like, is it the one with 2 moles? I don't think it is, but I will double check that for you. In fact, I have an answer key. Let's see what they say in the answer key, because I feel like because it's average, it would be the same. But what's this called? This is 13.3a. And that is question number 20-something. '28. They will all have the same kinetic energy because they're all at the same temperature. We were right. Okay, good. Good, good, good. All right, and I think that is it for this one. So we're going to move on to 13.3b. which is more of the same, really. I had this before I had the other one, so I was like, well, I'm not going to throw it away just because we have it. Yes. Yes. They shouldn't. The speeds should be the same because it's per molecule. Yeah. True, but we're looking at the speed per molecule, I believe. I'm going to go home and think about that just to be sure, but I believe the speeds should be the same. But I know this one weighs twice as much, but each particle weighs the same amount. So I'm going to go home and think about it and I'll get back to you. Does that sound okay? Okay, cool. Good question. All right. So here is nitrogen at 3 temperatures. So this should start looking very familiar to you. Yes, after we did that previous one. So we have the relative number of nitrogen molecules, and at the bottom, I don't know what's on the bottom. It just has numbers. It doesn't have a, it does not have a unit. So the peak of the curve represents the most probable speed of the gas particle. Oh, so these are speeds. The most probable speed increases as the temperature increases. So yeah, but we're basically summarizing what's happening there. So the peak shifts to the right. When you increase temperature, on average, the particles move faster. The right-hand end of the curve, which is indicated by the star, goes asymptotically towards zero. So in theory, you could have an infinitely fast particle for any of these curves, but you know, they peter out and you know. In gases at a higher temperature, the fastest particles represented by the star are faster than the fastest particles at the lower temperature. That makes sense, yes? Okay, so at the higher temperature, the end of the curve is further to the right. Sorry? The heat distributions? T distributions, probably. It's been years since I've done stats, so yeah. I would imagine that they have something to do with that, though. That would make a lot of sense. So the total number of particles is represented by the what under the curve? The area, yes. So that's our total number of particles. The curve, I don't know what I'm looking for there. Gets wider? Let's say gets wider. At higher temperatures. Since the curve is getting wider due to the highest speed, it must also get shorter or flatter in order for the area, the number of particles, to stay the same. And in case you are having trouble visualizing that, if we have less width, this is a 4 by 3, gives us 12. If we have this is a wider curve, this would be a 1, 2, 3, 4, 5, 6 by 2, and the area remains the same. And that looks like a really good place to stop for today. All right, we will pick up again next week and finish this off, and then we're going to move on to some reactions with gases. Thank you guys so much for being here. It's so nice to have people to talk to instead of just talking to myself. Rigel, I have other things for you, and we can hole punch those pages that aren't hole punched. Okay, so let's grab you a hole punch. Because what happens is I spill some paper. In the meantime, I will get you a binder clip because the pages won't come apart in order or not. Okay, and I also have a few other things. All right. So we need to talk about what units you have and what you don't have. So yes. So this is the gases answer key. Okay, the previous videos for gases are on our team. Atoms and electrons, it goes into a lot more depth. Okay, so we also do those. Also use yeah. And you're like, gosh, isn't that awesome? Yeah. Isn't it nice that you have a tour and you can put all of them? But you guys know each other, right? Yeah, I have. Yeah, so you might like, you know, make it a couple summer. Hey, wait. Yeah. So, what books do you actually have from me? Any of them? Like, nothing. So I'm going to get you all of the books of the grade 11 Enrich stuff. And you're going to write down your schedule. It's not working. Find you something that works. Oh, in fact, probably the only place I'll go to will be this one because it's right next door. Yes. Yeah, it's like probably. Yeah. Okay, perfect.